3 data points on the coordinate plane, the point 1, 1, the point 2, 2, and the point 3, 2. The challenge is to find the best straight line through all 3. We write this line in the form y equals c plus d times t, where c and d are unknown constants we need to determine. One candidate line nails 2 of the points but misses the third. Another candidate splits the difference more evenly. No single line passes through all 3 points. To pick the best one, we need a precise definition of what best means. And linear algebra delivers that definition by first admitting that no perfect solution exists. To turn this picture into equations, write the line as y equals c plus d times t, where c is the y-intercept and d is the slope. Now substitute each data point into this equation. At t equals 1, y equals 1 gives us c plus d equals 1. At t equals 2, y equals 2 gives us c plus 2d equals 2. At t equals 3, y equals 2 gives us c plus 3d equals 2. So we have 3 equations, but only 2 unknowns. In matrix form, we can write this as A times x equals b. The matrix A is a 3 by 2 matrix with rows 1, 1, 1, 2, and 1, 3. The first column is all 1s, and the second column contains the t values 1, 2, 3. The vector x is c and d, and the vector b is 1, 2, 2. Notice that A is tall and thin. It has more rows than columns. This is what we call an overdetermined system. 3 constraints, but only 2 knobs to turn. No values of c and d can satisfy all 3 equations at once. Here's the geometric picture. Every choice of c and d produces a vector AX in R3. All possible outputs form the column space of A, a 2-dimensional plane sitting inside R3. The column space is the set of all vectors that A can produce. Our data vector B lives in R3, but it doesn't lie on that plane. That means no exact solution exists. So what's the best strategy? Find the point on the plane that is closest to B. That point is the projection, P equals AX hat. The hat notation marks X hat as our best estimate, the closest we can get. The error, E, equals B minus P, and the least error vector is perpendicular to the plane. That perpendicularity is the key geometric insight behind least squares, back on the scatter plot. For any candidate line, each data point has a vertical distance to the line. Call these E1, E2, E3. Some are positive, some are negative. We need a single number to measure the total misfit. Summing the errors directly fails because positives cancel negatives. Taking absolute values works for preventing cancellation, but the absolute value function is not differentiable at 0. Squaring solves both problems. Define the total squared error, capital E, as E1 squared plus E2 squared plus E3 squared. In vector form, this is the squared norm of AX minus B. Squaring penalizes positive and negative errors equally. It produces a smooth differentiable function, and critically, it yields linear equations when we minimize, which is exactly what makes least squares so elegant. The minimizer x hat satisfies the normal equations. A transpose A times x hat equals A transpose B. The term normal here means perpendicular. This equation forces the error to be orthogonal to the column space. Let's compute everything step by step. A transpose is the 2 by 3 matrix with rows 1, 1, 1, and 1, 2, 3. Now we multiply A transpose times A. The top left entry is 1 times 1 plus 1 times 1 plus 1 times 1, which equals 3. The top right entry is 1 times 1 plus 1 times 2 plus 1 times 3, which equals 6. The bottom left entry is also 6 by the symmetry of A transpose A. The bottom right entry is 1 times 1 plus 2 times 2 plus 3 times 3, which is 1 plus 4 plus 9, equaling 14. So A transpose A is the matrix with entries 3, 6, 6, 14. Next, we compute A transpose times B. The first entry is 1 times 1 plus 1 times 2 plus 1 times 2, which equals 5. The second entry is 1 times 1 plus 2 times 2 plus 3 times 2, which is 1 plus 4 plus 6 equaling 11. So our system of normal equations becomes 3c plus 6d equals 5 and 6c plus 14d equals 11. We solve by elimination, subtract twice the first equation from the second. That gives 0c plus 2d equals 1, so d equals 1/2. Now back substitute into the first equation. 3c plus 6 times 1/2 equals 5, so 3c plus 3 equals 5, meaning 3c equals 2, and c equals 2/3. Therefore, the best fit line is y equals 2/3 plus 1/2 t. We found the best fit line through linear algebra. Now let's take a completely different rule, calculus, and see why both methods agree. Write the total squared error, E equals the quantity c plus d minus 1, all squared, plus the quantity c plus 2, d minus 2, all squared, plus the quantity c plus 3d minus 2, all squared. Each term corresponds to one data point. To minimize E, we take partial derivatives and set them to 0. The partial of E with respect to c is 2 times the quantity c plus d minus 1 plus 2 times the quantity c plus 2d minus 2 plus 2 times the quantity c plus 3d minus 2, all set equal to 0. Divide everything by 2 and expand. We get c plus d minus 1 plus c plus 2d minus 2 plus c plus 3d minus 2 equals 0. Collecting terms, 3c plus 6, d minus 5 equals 0, which gives us 3c plus 6, d equals 5. Now for the partial of E with respect to d. By the chain rule, each term picks up an extra factor, the coefficient of d inside that bracket. That's 1 for the first term, 2 for the second, and 3 for the third. So we get 1 times the quantity c plus d minus 1 plus 2 times the quantity c plus 2d minus 2 plus 3 times the quantity c plus 3d minus 2 equals 0. Expanding, c plus d minus 1 plus 2, c plus 4, d minus 4 plus 3, c plus 9, d minus 6 equals 0. Collecting terms, 6c plus 14d minus 11 equals 0, giving us 6c plus 14d equals 11. Now look at these two equations. 3c plus 6d equals 5 and 6c plus 14d equals 11. These are exactly the same normal equations we found from the linear algebra route. Two roads, linear algebra and calculus, lead to the same destination. The deep reason is that squaring a linear expression and then differentiating always produces a linear equation. Now let's see this solution on the scatter plot. The best fit line is y equals 2/3 plus 1/2 t. At t equals 1, the line predicts 2/3 plus 1/2, which is 7/6. The actual data value is 1, so the error E1 equals 1 minus 7/6, which gives us negative 1/6. At t equals 2, the prediction is 2/3 plus 1, which is 5/3. The data value is 2. So E2 equals 2 minus 5/3, which is 1/3. At t equals 3, the prediction is 2/3 plus 3/2, which is 13/6. The data value is 2. So E3 equals 2 minus 13/6, which is negative 1/6. Now we square each error. Negative 1/6 squared is 1 over 36. 1/3 squared is 1 over 9, which equals 4 over 36. And negative 1/6 squared is again 1 over 36. Adding these up, 1 over 36 plus 4 over 36 plus 1 over 36 gives 6 over 36, which simplifies to 1/6. This is the minimum total squared error. No other line achieves a smaller sum of squared errors. Now let's see the vulnerability that comes from squaring. We add a single outlier at the point 2, 10, far above the original data. Watch what happens when we recompute the best fit line using all 4 points. The line lurches upward toward the rogue point. This happens because squaring amplifies large errors disproportionately. The 3 well-behaved original points produce tiny squared errors. The smallest is 1 over 36, approximately 0.03, and the largest is 4/36, approximately 0.11. These are all fractions of 1. But the outlier sits about 8 1/3 units from the original line. Squaring that gives roughly 69, call it around 64 if we round down. That single point dominates the entire fit, contributing far more to the total squared error than all 3 original points combined. This is the Achilles heel of least squares regression. Statisticians counter this weakness with robust methods, such as least absolute deviations, which use the absolute value of errors instead of squaring, or Hilbert loss, which blends squared error for small residuals with absolute error for large ones. The key takeaway: always plot your data before trusting the formula. Least squares is far more than a textbook exercise. The normal equations A transpose AX hat equals A transpose B appear across science and engineering, in linear regression, GPS positioning, signal processing, and machine learning. Wherever an overdetermined system needs the best approximate answer, this framework applies. Let's review the 3-step structure. Step 1. Recognize that the system has more equations than unknowns. It's overdetermined, so no exact solution exists. Step 2. Reframe the problem. Instead of trying to solve AX equals B exactly, minimize the squared norm of AX minus B. Step 3. Solve the normal equations to find X hat. When perfection is impossible, least squares delivers the mathematically optimal compromise, with the caveat, as we saw earlier, that outliers can undermine the result,